Okay, ladies and gentlemen, we're going to begin now. But first, before I start, I'd just like to say, Partif, you must really love this. We love to have you here, but it's really, really early in Denver. So, welcome. I see there are people here from Australia as well. So, you guys, people from Beirut, Chile. So there are people who are very, very early. There are people who are in the middle of the night. So obviously, and this is something we've known for a while, it's a subject that that interests you a lot, and that you've been working on for many years. So thank you very, very much for joining us today. Today, we were going to be talking about heat for the solar heat, rather, for the commercial and industrial part of the energy debate, I suppose. So one of the things we know is that electricity is only about, say, 20% or 30% of the energy we need. I think it's 28. I think Martin and Guillermo can probably tell us more specifically. But actually, the heat that we use, the energy that we use to heat up for industrial processes is much, much higher than that. It could be nearly 50%. So this is why it's very important that in a universe where we're decarbonizing, we're looking at these commercial and industrial processes and decarbonizing them, because they are going to be, this heat is going to be the one that makes the biggest difference in terms of carbon reduction, but it's also at times the hardest people to convince. So with us today, we've got two experts on the topic. So I'd like to ask first, Martin, if you can please introduce yourself briefly and where you're joining us from.
Everybody.
Sorry, Martin, we can't hear. Oh, now.
All right. Can you hear me?
Yes, now we can.
All right. So good morning, afternoon, evening, everybody. My name is Martin. I'm the commercial director of Protarget AG. We are based in Cologne in Germany, and we are specialized in industrial process heat and steam generation.
Thank you very much. We're going to hear from Martin shortly. And Guillermo, please tell us how to pronounce your name properly, and also introduce yourself.
My name is Guglielmo. Possibly my mother didn't know that I was going to entertain an international career, so this name is very difficult to pronounce. I am calling you from Geneva, from TVP Solar. We are the producer of a new generation of solar thermal flat panel, the high vacuum flat panel that are suitable for energy production at industrial temperature up to 180 degrees.
Thank you very much.
And I am also, I would say, let me say, vice chair of the European Solar Thermal Technology Platform, that is a European body dedicated to the promotion of solar thermal.
Thank you very much, Guglielmo. And I joined on the club of my mother didn't know I was going to have an international crowd, so I completely understand you. They are difficult names. However, we're here today to learn a lot about solar steam for commercial and industrial applications. So please, Martin, if you can share your presentation, I'm really looking forward to hear. As you know, this is something a lot of people have been working for a long time. And we're getting closer. There is more and more interest around this. So please, if you can share your screen.
Okay.
And whilst Martin shares his screen, I just want to remind you guys of a few things. So many of you have already been in our webinars before. We'll hear a presentation from Martin, then a presentation from Guillermo. And then finally, we'll take questions, as many as we can at the end. We are recording this session, so don't worry, the recordings will be available, and you will be able to download the presentations as well. So go ahead, Martin.
Yes, thank you. So
for the questions, make sure you send them through the Q&A box at the bottom, okay? We'll take them from there.
All right.
And keep introducing yourselves from in the chat. I see there are people from literally everywhere. Are you having problems, Martin, with the screen?
We're coming. Give me 1 second.
All right. So maybe we can send a little bit of a heads up, like Brussels, The Hague, Berlin, people from Germany, India, Nigeria, Ghana, Chile. Oh, you're ready. Perfect.
Excellent.
You can see everything and we can hear you. So go ahead.
All the country with lots of sunshine. You're welcome. So, yeah, thank you everybody once more for joining us here. as I've been already introduced, my name is Martin. I'm the director of Protarget AG here in Cologne, in Germany. Our company is specialized in industrial process heat and steam generation. Here in Cologne is where our design offices and prototype manufacturing unit are. We have a second unit in the east of Germany, in Chemnitz, where we produce vacuum receivers for parabolic trough collectors. We also have a local manufacturing resources in India and in Chile, which also tells you something about two of our key markets. What is important is that our technology, as we are approaching the industrial sector, is approved to various standards, for example, European Pressure Directive, Indian Boiler Regulation, and also empaneled for the Indian market, which for some of the customers is important because it makes our technology eligible for Indian subsidies. We have built and operating commercial plants in Germany, Cyprus, India, and also Brazil. And we have currently new projects in development and construction in Chile, some more in Cyprus, Jordan, and India. So in summary, what is our objective here at Protarget is to supply solar steam boiler systems for process heat and steam application. And we are an engineering unit to provide CSP services for all relevant projects worldwide. Something about our technology, as briefly introduced, we using the parabolic trough technology. For this, we have developed a collector module that is specifically designed for industrial application in harsh climatic environments. It is a parabolic trough collector with 3 meters aperture, and it contains basically all the technical features you are probably well familiar with from the large-scale power plants for utilities and electricity generation. In our case, it is designed for industrial process heat supply with temperatures of up to 420 degrees, which is probably one of the key features of this module. As Berlin has briefly introduced, what is our target market? It is the heat demand of the industry, and that's the majority of the energy that the industry is in need of. It's 3/4 of the energy consumed in the industry is for process heat and steam. The sad news, or for us, the good news is 90% of that is still generated with coal, oil, and gas. This demand, this process heat demand, is continuously increasing. In particular, in development countries where more and more industries, for example, the food industry, is picking up. What is the temperature range, or what are the branches and the temperature ranges that are in demand of this thermal energy? So most thermal processes in the industry are in the range of 100 to 150 degrees. In order to provide those temperature levels, conventional fuel boilers are typically operated in the range of 150 to 200 degrees. So this is our enemy. Yeah, the conventional fuel boiler that is burning dirty, heavy fuel oils, mazout, diesel, gas, wood, you name it. This is the technology we want to substitute. How do we do this? We install rows of curved mirrors, parabolic mirrors. We use the sun's energy to heat up a heat transfer fluid to 400 degrees and more. With this heat transfer fluid, we basically go into conventional heat exchanger, steam boilers, and provide steam at any temperature and flavor the customer requires it. Obviously, since we are primarily generating thermal energy, we are able to store it and provide steam and heat also during the night or in periods of bad weather. Because even in the Atacama Desert, we will find days without sunshine. Rarely, but it happens. Such a steam boiler system is typically integrated in parallel to the existing infrastructure, steam infrastructure of the customer. This means the solar system acts as a fuel saver rather than completely replacing the system. So the focus actually now of my presentation is to show you some details about the economy of such a fuel saver system. And for this, we compare a conventional steam boiler with a solar boiler. So here you have a direct comparison. On the left side, a good and fine German steam boiler that you might find in any place on the world, in the backyard of any factory. It is a very good piece of equipment. Yeah, don't get me wrong on that. It has low investment cost. It operates with oil and gas, which is a fuel that is widely available. It has a standardized size. And most important, it is proven and reliable. So nothing wrong about a conventional steam boiler. The disadvantage, though, is it has high operating costs and it emits carbon dioxide. And this is the point where we want to angle it. We want to substitute the fuel, not the boiler. We want to substitute the fuel with a solar boiler. So the solar boiler, on the other hand, is then integrated in parallel to this boiler, acting as a fuel saver. We provide steam directly into the infrastructure, which has as a result that the conventional fuel boiler reduces its fuel consumption significantly. Here we have an example of a 5-ton boiler, which is a quite typical size in the industry. The boiler provides steam at 170 degrees, 10 bar. It runs 10 hours a day, 5 days a week, which results in 2,200 operating hours per year. On the left side, the fuel boiler has fuel costs of 700 euro a ton. You find countries where fuel is more expensive. You find lots of countries where the fuel is less expensive. But this just to give you an average value. The annual cost, and this is just the fuel cost of the conventional fuel boiler, would then result in 550,000 euro per year. The annual operating cost of the solar system would only be 50,000, because it is down to cleaning the mirror and maintaining the system, and that's it. So this results in a cost saving of €500,000 per year. To go a bit deeper into the economics of a solar thermal system, what would it mean for you, for example, as a customer? Let's stick to the 5-ton per hour boiler, the solar boiler. This would mean investment costs of about €2 million. Obviously, banks are involved in this. You're going to lend the money for an average loan of 5% per year. We have the 50,000 euro annual O&M cost when we assume the O&M cost increases 2% per year. The fuel cost with 700 euro a ton also increases at a rate of 2% per year. And in summary, this results in a fuel saving for you at 550,000 euro per year. Not to be forgotten, the CO2 reduction, almost, and this depends obviously then on the fuel you are using, of almost 3,000 tons per year. And more important, the investment is paid back just on the fuel savings in 3 to 4 years, and generating you a significant cost saving in the following years. So in this result, in this graph, as you can see, in year 10, you have generated net savings of 4 million euro. The economy of a CST system is mainly driven by the fuel cost. And as said before, the fuel costs are quite different in the various countries. This graph shall give you an idea on the amortization of the system in relation to the fuel cost. Obviously, there are countries where fuel is heavily subsidized, and there are countries that have market values for the fuel they are using. But this graph shall give you an average overview what a CST system can generate you in terms of payback period, independently of the fuel cost. So I'm already coming to the summary of my presentation. The message is in industrial areas where steam is produced in a conventional boiler, may it be powered with diesel, HFO, mazout, you name it, at, for example, 700 euro a ton. We are looking at steam generation costs of 50 euro per ton. With our CST technology, you are able to generate steam at 10 euro a ton, which obviously is a reduction in steam cost of about 80%. We are also, as a company, we are also offering here O&M agreements or energy contracting model to take away any financial burdens from you or any technical risk you might see in this. This technology is not designed for Germany where it is produced. It's designed for desert. It's designed for the Atacama. It's designed for harsh climatic environments. And it will last 20 years in this environment. So this protects you from any further fuel price increase or any other externalities such as carbon taxes and so on. So my message is, where sunshine and land is available and fuel has a value, the CST technology is the most suitable for thermal energy generation. Thank you very much for your attention, everybody.
Thank you very much, Martin. I suppose after hearing your pitch, which is really good, very convincing, the question is, you must not be keeping up with the demand that you have. But anyway, we'll save the questions for later. If you can please stop sharing the screen. Yep. And Guillermo, go ahead, you share your screen and you give your presentation. It is insane when you look at the numbers, you know, just how advantageous. So let's hope we can break a little bit of the inertia of these companies, you know, in the way they think about their investments. All right, you're ready? Go ahead.
Yes, I'm up. Hello everyone. As I said, I am going to introduce to you our TVP Solar system. We are bringing this technology to the market after 10 years of research and development, and after we built a fully functioning production unit 2 years ago. So this is to be considered a new generation of solar thermal flat panels insulated by high vacuum inside the box. So it's a rather new, I would say, breakthrough product that will enable the production of solar heat for industrial process and is designed for large-scale installation. So what you are seeing on the screen now is an actual solar field. You see it looks very much like a traditional flat panel, but its performance are in a completely different range. These solar collectors have a particularly high efficiency.
Guillermo, just 1 second, please.
Yes.
Are you moving the presentation forward?
Not yet. Not yet.
No, not yet. Oh, okay,
Don't
thank
worry
you.
about it.
Perfect.
I'll tell you when I do. I'm just focusing on the fact that the product has been designed for industrial application and for temperature between 60 and 180 degrees. And the main difference with what, now I am moving the presentation. Do you see the new slide? Yes. So
yes, all perfect. I just thought you were moving them, we couldn't see them, but that's fine.
The main difference with what has been presented by Martin is that the flat collectors, I mean any flat collectors, ours included, can collect very efficiently both the direct light and the diffuse component of light. So we are not just able to produce such temperature in very dry climate with direct light, but also in foggy, dusty, and cloudy climates. And I want to jump in immediately into the issue of the integration with the industrial process, because this is the kind of worry that most of industrial operators and adopters of our technology are showing. And so where do we put our heat? So what you are seeing is an extreme simplification of an industrial process heat circuit. Typically, steam is produced at 10 bar and distributed all over the factory, and then used at different temperatures. So in reality, the consumption of heat does not really happen with steam at 10 bar, but rather at lower temperature, sometimes in the form of hot water, sometimes in the form of low pressure steam. We are facing such cases on a daily basis with our clients. So where do we can integrate the solar heat that we produce with our solar panels? Basically at the level of the application for hot water up to 180 degrees. I will show you a case which we are actually operating right now at 180 degrees. Or we can simply integrate the heat going back into the boiler by raising the temperature of the water. So this is a typical boiler feed water preheating. We believe that this makes it as simple as possible to integrate a solar field into an existing process and to retrofit existing industrial sites. Because, to be clear, our solar field works in a closed circuit. So we provide the heat to the final application by means of a heat exchange. So in any case, the user becomes independent by the solar field and can only use the upside of our energy production to reduce their fuel consumption. I don't like to show very much these graphs, but it's important for me to tell you a couple of things. First of all, the collectors are certified in their performance. So as many other solar flat and evacuated pipes, the performance that we claim is not only something that we measure, but it's been validated and certified by third parties. In this case, in particular, by the Solar Key Mark the organization. So in this case, what I'm showing you here is the efficiency of the panel at different temperatures. And I'm doing this in comparison with other certified products, in particular flat plate collectors or evacuated tube collectors. So you see that most other certified products stop at 100, maximum 120 degrees. I mean, their certification does not go above that threshold. And instead, the TVP Solar collector goes up to 180 degrees. And there is a significant performance gap. I mean, at industrial grade temperature, like 100 degrees or so, with the full sun, which means with the full daylight at midday, our collectors are already more performing by 25 to 70%. So for example, 70% compared with a flat plate collector. And then of course, we can go higher in temperature. But I believe that what is more meaningful for most final adopters is what happens when the sun is not full, when we have average daylight conditions. Because this is what we actually achieve over a full year. We have conditions of good sun and average sun. And when the sun is not at full capacity, when we are at half than that, then you see that the big difference in energy production. In the end, all of us, what we care is the energy production. And in this case, you can see that the high vacuum inside the panel makes a big difference. Already at 120 degrees, we are between 3 times or 10 times, depending on what collector we are comparing to, with the traditional products. This is an example of one installation that we have already, we are operating since almost 1 year. This is in Abu Dhabi, so it's a high radiance country. It's not a very large solar field, 150 kilowatt, but it works every day at 170 degrees for a rubber factory, making a real difference in terms of energy consumption. And these are measured data. The solar average temperature, the solar average efficiency over the year is 37%. It works only during daytime. And what is most important is that this solar field basically does not need any cleaning. So we were talking about operational cost. The solar field has very low operational cost because basically it does need only some electricity to let the pump circulate the fluid, but it does not really attention and cleaning. Just to give you a clear number, the difference between the expected production of these collectors in this particular case and what has been actually measured is only 8%. And this 8% less production depends on the fact that there is dirt accumulated on the panel because the panels are never clean. And so, but this is a trade-off that you can accept, if you like, in return of the simplicity of this system. This is another solar field that we are building right now, and is in France, so in a very different location, situation, and it's a larger one, it's 1 megawatt, and will feed hot water at 140 degrees in the return circuit to the boiler for a meat factory. So in this case, you see the energy yield is about, the energy savings is about 130,000 cubic meters of gas to the factory, and it will work extended daytime, like 12 hours a day by means of a thermal storage. The thermal storage in this case is just a tank accumulating hot water. So there are measurable results of this technology, and we measure it in terms of savings. And these savings are substantial over the year. This is a case we have elaborated, for example, not in a very hot climate, but in a European climate, and basically in Italy. And so this is something that you can achieve by complementing a typical hot water boiler or a steam boiler with solar. I don't want to go into more detail of graphs because I hate them. But you would be curious to know about the the OPEX and CAPEX of such a solar field. So I'm putting them right there. I mean, typical setup that we would suggest is to go around 3,000 square meter of panel that would produce like between 1,800 and 2,000 kilowatt, this depending on the climate we are in. And the CAPEX for such a system would be around 1.5 million, and their OPEX is about 3.1 euros per square meter per year, so about 9,000 euros in this case. The cost of energy resulting from such a setup, without considering any subsidies or government support, would be between 25 and 40 euros per megawatt. That I believe is today's cheapest source of energy cost, that is natural gas. The economic assumptions between this, behind these numbers is that the solar plant lifetime is 25 years. And, and without including any facilitated financing. Of course, you might ask, how do you know that the plant will last 25 years? We have submitted our product to accelerated stress test, both for corrosion and for thermal cycling, and so now we are confident that the duration of the product is 25 years. And by the way, we provide guarantees for the panels for 20 years. So just to go on quickly, I just quickly want to show you that we have also the cooling application, because we have been talking about commercial. I mean, the topic should be also commercial application. And we have already established some application by using absorption chiller fed by our solar field at 90 degrees or 165 degrees, depending on what kind of chiller we are using. This is a practical application we have already established, for example, in Kuwait, and it can provide substantial savings in terms of electricity, for example, for large non-residential buildings. In the case of, but anyway, it's in competition with the very efficient electrical cooling systems. Therefore, we believe that is most suitable for very hot countries, which will use the cooling service for the whole year. The alternative to this, let me see if I have the case. The alternative to this would be to have a dual use for the solar field. For example, in the case of European climate, we are proposing the solar field in a dual configuration that can provide hot water, therefore space heating during the winter, and space cooling during the summer. I'm not sure if I stayed in the time. I hope so. And of course, I am eager to take your questions. And thank you very much.
Thank you very much, Guillermo. Yeah, you've done a great job. And I'm going to ask you just to stop sharing so that people can see you a little bit better. And we have a lot of questions. So if you think, if you agree, we'll just go right ahead for them. If you want to open and you see any specifically you like to answer, also go for them. I've marked some, I've prioritized some that I think are important. And also one thing, we'll take about maybe 10-15 minutes. Usually more questions come in as we're going. So, you know, we'll see how we're doing. All right. So one of the questions here, let me see if I can find it because I had marked it. Says, do you implement, sorry, it's just move on. Energy contracting models in India? I think this is for you, Martin, because it was a question that came around your time. No, we can, oh, now.
Now? Okay, can you hear me? Yes, we implement energy contracting models also in India. Straightforward, yes.
What is the minimal, this is for the two of you, thermal capacity of the solar field for which CSP is competitive in comparison to a conventional boiler? So we're talking about scale here.
Starting the answer with it depends. I don't like this, it depends, but it really does. It depends on the solar radiation and on the fuel cost you have. But let's say our technology is geared up for industrial applications, and for us, this starts at a capacity of half a ton of steam per hour, so 500 kilogram of steam per hour. Technically, it works smaller, but economically, it starts to become difficult.
You know, this question has been answered in many ways. It's been asked in several ways. So someone here asked, what are the minimum sunshine values, which DNI, I suppose, is the right thing to say here. Valuable, necessary, so what is the minimum DNI that we need? What is the fuel value to make CSP competitive? So they're trying to ask you the same question in different ways. So I suppose you guys, if you want to, explain.
I can try to frame it, at least for our technology. It's really a combination of the available irradiance and the operating temperature that you are looking for. For example, if you want to be competitive with any kind of fuel with our technology, even with the cheapest one, if you are, for example, in a European style climate, like 1,300, 1,400 kilowatt hour per square meter of GHI and not DNI, then I guess that you should stay in the range between 80 and 110 degrees. If you are, for example, in the Middle East or something like that, then you can reach higher temperature and still be competitive with the local fuel that typically is more expensive than the gas in Europe. So it's really a combination of these three factors. I mean, location and fuel costs and sites, of course. But I want to answer the question on sites. Our system is designed to be implemented from 300 kilowatt above. Not lower than that. But generally speaking, the big threshold in economy of scale happens when we are talking about 5,000 square meters, therefore about a couple of megawatts, couple to 2.5 megawatts.
Martin, do you want to add?
Yes. One of the question was at which solar radiation does it make sense to install this technology? Let's put it that way. A few months ago, let's say half a year ago, my answer would have been it starts at 1,500 DNI. DNI is direct normal irradiation, and that is probably something we find in the Mediterranean, North Mediterranean areas. Then, end of last year, for example, the German government has talked about a carbon tax, which suddenly moved that scale a little bit up. And then, beginning of this year, they have even increased the value of this carbon tax. So, the benefit of installing a carbon neutral technology has suddenly increased, and suddenly we can live with lower DNI. So, in summary, now it would even make sense to install it in Germany.
Okay. I have to say also, just this I suppose is bad news in some ways. It seems like the price of gas is going to go down again because of supply. It looks like a lot more supply is going to be made available. So we'll see. I mean, this is, this is what people are talking about right now in the news, but we will see how it goes. So that could again affect the other way around, I suppose.
Of course.
Okay. Hang on, there were some more questions. Okay, what about space requirements? Can you give people like an idea of how much room they need for the systems and whether they can be placed on the roof?
Well, in our case, surely they can be placed on the roof. The average weight of the solar field is 50 kilograms per square meter. And the footprint is basically 1.8 times the actual collector's gross area. So let's say for 1,000 square meter, you would need 1,800 square meter of rooftop.
Martin?
In our case, the technology is primarily designed for ground installation. We can be mounted on the roof, but typically your roof cannot is not suitable for us. Not in terms of weight. A collector is only about 1.6 tons, but the wind load is the issue. So one row of our parabolic trough collectors is about 260 square meter, and you imagine in the morning the collector is placed towards the east, and a wind load would then imply quite heavy loads to your structure. So it's designed for ground mounting, and we need about 4,000 square meter per ton of steam.
1,000 square meters per ton of steam.
No, 4,000 square meters.
1,000 square meters per ton of steam.
Yes.
Okay. Okay. Is it feasible to produce cold instead of heat?
Well, I guess I showed some application. It certainly is. My recommendation would be to do it in a special situation. For example, in the case that we developed in the Emirates and in Kuwait, these areas have problems with the electrical grid. So it's often the case that the final user cannot access enough electricity to power their chillers. In this case, I believe that we have really a big advantage because we can make the building independent, or the factory or production unit independent from the grid.
What about you, Martin? Do you want to add?
Yes, basically there are two more technologies to be added to the CST technology, which we have installed, for example, already in India. One is powering an absorption chiller, multi-stage absorption chiller to provide cool energy for cold storage. This is well possible. The second technology, which is also quite interesting, is industrial wastewater treatment. So in this case, the CST technology is powering a membrane distillation unit. Both technologies are quite mature, well familiar in the industry, or well established in the industry. Depending on the solar resource that is available, they may create significant benefits to the company using it.
Okay, a question. It says for TVP, but you know, I'm gonna, I don't know. It's in reference to your presentation, I think. Why is the efficiency of the system in France more than 50%? Is it so much higher than Abu Dhabi, which is 30-something%?
The reply lies in the efficiency curve that I showed you during the presentation. The higher the temperature, the lower the efficiency. In the Emirates, we are running the solar field at 180 degrees, 170, 180. And that is the maximum range of operation for our collectors. Therefore, we must give something back in terms of efficiency. But in France, as we are running between 90 and 140, the average temperature in the solar field is the average between 90 and 140, so I guess 110, 120, and the efficiency is higher according to the curve for CSI.
Thank you very much. Okay, how does heat storage work? What is the medium, you know, how long can it last? How does it work? Just give us an idea. How long does it last? I don't know.
Well, we use thermal storage only to extend the operations of the solar field over the day. So we're not talking here about seasonal storage, which are very popular in district heating applications. But typically we can go up to 20 hours a day, and the storage media is water. So we can either put a pressurized storage tank with the hot water, or in the case of lower temperature like 90 degrees, even a atmospheric pressure storage tank properly insulated. So the duration can be several hours, but I would not suggest to do more than that.
How about you, Martin?
Depending on the application and the system capacity, there are 3 different storage technologies we are using, we have built and that are in operation. One, give you an example, our project in Cyprus, where we supply high temperature steam to a fruit juice factory 24/7, so around the clock. We are using a concrete storage. This is the right technology for that specific application in terms of costs and in terms of dispatchability of the energy. For a project in Brazil, we were using a thermal oil storage because there the request was to be or to have a storage that is more reactive. Yeah, so the charge and discharge of a thermal oil storage is quite rapid. The third project, we've been using a water storage, a large water storage with pressurized hot water. So depending on the application and in the end then on the economy, there are various storage technologies possible.
Okay, what about textile? There is a question here about textile. Is there any examples of such applications in textile that you know of?
I have read the question. I'm happy to answer, and I share the opinion. And I asked myself the same question: why is the textile industry so reluctant to use any form of renewable energy? Honestly, I haven't had an answer up till now yet. It is sad. It is very sad. It's a industry that is using quite a lot of thermal energy, hot water, steam in all sorts and flavors. One of the answers might be that the textile industry typically is gathered in industrial zones. So the factories are, quite in close approximation, not much space available, not even on the roof. If you go to Pakistan and parts of India, you find people living on the roof. So how do you want to install a solar system there? But that is not, to me, the main problem. It is more the customer's problem. The customer is the European or the Western, the big brands buying these textiles. They take care of the first level of the supply chain, but the supply chain has 20, 30 levels, and they don't look at the steps behind. Yes, there are some exceptions, don't get me wrong, but so far, and I'm standing up for this opinion, the brands do not take care how their textiles are being produced.
Well, in our case, we didn't have the disappointment about the textiles because we didn't have the chance to interface with the textile industry, although we believe that they have a big shot to solar thermal energy. We have more experience with the food industry, and they are responding well. In general, the biggest problem is to get confidence from the plant directors and technical operators, because they are mostly concerned about integration issues and the production being in some way perturbed by a different source of energy, which is of course dependent on the weather and on the climate. I must say that the way we have approached this so far has been successful in the sense that the fact that basically we are separated in terms of circuitry from the heat circuit of the factory provides a sufficient safety to the plant operator. But this is a work that needs to be carried out at a general level in all the industries to help them understand that the risks are really not significant compared to the advantages.
Thank you very much. To be fair, I just wanted to say about this fashion thing. I mean, fast fashion is very quickly getting into like the bullseye in terms of campaigning for change. So my guess is that in the next 2 decades, because it's not going to happen overnight, things are going to change, and they're going to change a lot indeed. A lot of the companies, that have made climate announcements or climate protection announcements. They're all started with the obvious, you know, changing their shops to renewable energy, but there is also a commitment to get all the way through, and the supply chain will eventually also be touched. So I think we can see we will be able to see a lot of change in fast fashion particularly, which I suppose in terms of textiles will be like the most turnover and one of the biggest clients. So at least I am positive that this is going to change in the next few years. Okay, how competitive would these solar systems be for low temperature compared to conventional systems? Is there an optimum range? Who wants to take this question?
For low temperature, Martin, I guess I'm going to take the question. So if we're talking about temperature between 50 to 90 degrees, then it is already competitive. I mean, it all depends on the return temperature of the circuit we want to heat up. In particular, when we are in low irradiance countries, for traditional flat collectors or evacuated pipes collectors, it is very difficult in low irradiance areas to raise the temperature above 50 or 60 degrees. Unless, of course, during a few days over the summer, this is always possible. But if we're looking at an average production over the year, I believe that in this case, we can have a very good performance. In fact, one of the applications that is not the topic today that we are particularly looking for is the solar district heating that is typical of low irradiance areas and is requiring temperature between 80 and 100 degrees. And in these cases, we are showing extremely high performance that is not available with any other system.
Okay, I think the last one I'm going to ask, unless you guys want to answer any of them particularly, there will be 8 open now when I'm done. It's also nearly 5 minutes to the hour. So what are the O&M costs on a yearly basis for your systems? I'm going to ask for the two of you. There's actually a couple of questions about this, about O&M cost, time, intervals. So if you can give a little bit of information, then that'll be really welcome.
Okay, in our case, the parabolic trough, the operations and maintenance of a parabolic trough system is down to cleaning the mirrors. This has to be done, but obviously you don't need to hire rocket scientists to do that. But it has to be done correctly. You don't need to have a robot, you don't need to have a machine. You need to have a guy that can operate a pressure washer, and he needs to clean the mirrors depending on dust or pollution level in the area 1 to 3 times per month the mirrors. And these are the main O&M costs of the system.
Well, in our case, in European type climate, we do not advise to clean them ever, in the sense that the rain is enough to clean a flat panel when it rains. In a dusty environment, we have run a test in Saudi Arabia, not cleaning the panels for 1 year, and after 1 year, the loss in performance was 7%. So the panels were supposed to run at 47% efficiency, and they were running at 40. So this is a significant data measured by Saudi Aramco that shows that basically it's up to you. If you want to clean them, you spend some time and some effort, but no water, because it is cleaned with brushes and dry cleaning. So, but it depends if you are looking for that additional excess performance or not. The rest of the cost for operation and maintenance, we estimated around $3 per square meter. And they are related to circuit stops and eventually periodic maintenance, I don't know, repairing some pipes, not for the panels itself, because the panels, in the case of failure, they are to be replaced. And so you can just isolate a small portion of the solar field and keep producing with the rest. So you will not have meaningful losses in terms of energy production and no stops. And this is the only possibility for additional cost. But as I said, the panels are guaranteed for 20 years. So basically even that will not be a cost. So $3 per square meter. It's a good matrix for this kind of costs.
Belen, there's, if you may, or if you allow, there's one question.
Go for it. Okay, go, answer it.
Marcos has the question, can you indicate possible application example at temperatures above 400 degrees? Very good question. So first of all, we run the thermal oil in the parabolic troughs as high as possible. For example, this is an advantage when we store the energy. So we store the energy at the highest possible temperature level to increase the density. On the customer side, typical applications in this range are the ceramic cement industry, processes called calcination. This is more, let's say, burning processes. But the whole range of ceramics and cement industry, gypsum, for example, which is a big industry, they are operating at temperatures even up to 750 degrees. So imagine you need 750 degree drying. The solar part of it can already provide you the first 400, 420. Yeah. So simple math, you will reduce your fuel consumption by half.
Well, thank you very much. I think we're out of time because it's literally 2 minutes. So I'd like to thank both of you, Martin, Guillermo. I will learn to say your name very well. Thank you very much for your time, you guys. And I think we've learned a great deal today. I think most important message out here is that this is not a pipe dream. It's not something that could be available in 50 years. It's available today. And by the sounds of things, oftentimes quite competitive. So let's hope, you know, that all of this pressure that we're seeing now over like the decarbonization starts to open up the eyes of many industrialists, you know, towards, you know, the capacity of renewable energy and solar in this case, of actually pick up a lot of the mantle. So because I think in the end, it will be good for everyone. So thank you very much, Martin. Thank you very much, Guillermo. And
thank you all.
Thank you, everyone. See you next time. Bye.
Goodbye.
Thank you. Bye-bye.